Right, folks, a very warm welcome to Support Vector's weekly paper reading. For those of you who are new here, especially, we have this tradition that we continue, and we have continued now for a couple of years. Every Wednesday, California evening at 7 p.m., we do read one research paper or discuss one topic or do some coding exercise or something like that. So recently, we have mostly focused on taking some recent development and reading the paper. The topic of today is this paper, Tokenformer, Rethinking Transformer Scaling with Tokenized Model Parameters. This is a very interesting development. It addresses a key question. Today, it's becoming harder and harder to scale up transformers. When we try to scale transformers up, let's say you just trained a model which was, let's say 100 billion parameters. Now you want to go to another model which is even bigger, 400 billion parameters or something like that, something to that effect. What you would typically do is you would go back to the original data and you would get hardware, and you would start training that model from scratch. So a close analogy is that if you want to add a few more rooms, expand your house, and add a few sections to it, instead of adding a few sections to the house, you essentially demolish it and start all over again simply because you had to add a wing to the building. It's not really efficient, and that's the analogy. Today, we don't scale models. The neural scaling laws, and I will write it down just to give a background. The neural scaling laws say that to have a more performing model, a more capable model, you need to, in a particular way, there are ways like insular, optimal, and so forth, but there is a particular way in which you could scale three factors together. You would scale the data, pre-training data. You would scale the compute, think in terms of flops, how many floating point operations it would take to train the model, which roughly speaking means how much hardware do you bring, how many GPUs do you bring, and for how long do you train. That is what flops ends up to. So it basically, corollary of that is lots of GPUs and lots of compute steps. So if you bring both of these, then you can successfully train a larger model, and it'll perform better. Now, so these are the neural scaling laws. I'll put it S with some because the way it's split. So this is the neural scaling law, and there's some minor caveats to it. Like, for example, the quality of data matters. What kind of data you bring for training. For example, one of the papers that we covered many months ago was the textbooks is all you need. The message there was, instead of just bringing in lots and lots of data, let us pay attention to the quality of the data. And so that did make an improvement. Then at the same time, in the compute aspect or in the model aspect itself, people do all sorts of optimizations. For example, they may cache some intermediate results and so on and so forth to make scaling up or computes more efficient. But broadly speaking, when you pre-train a model, so applicable to pre-training, foundation models. Now, when you, so there are two ways to get a model and then improve upon it. One is you can fine tune it, and then we have been doing a few LoRa-based methods in the past, or you could do inference time optimizations, like better prompts, agentic reasoning, and so on and so forth, RAG. All of these I would put in the category of clever ideas at inference time. This paper is interesting. It it sort of covers territories in some sense. It sort of has a feel of a mixture of experts. If you remember, a mixture of experts was an alternative way to scale models to make them smarter. You take lots of small models and you put a routing network. So suppose you put a routing network or neural net here, and then you decide which of the experts do you are going to route the answer, and finally you get the output y hat. So this is your mixture of experts approach. The role of the routing network in a mixture of experts thinking is to just look at the query, the input, and ask which is the right expert appropriate for answering this question. And then you can use much smaller experts and get away with it. So that's why we use the word sparse mixture of experts. Again, a way to scale up and get a better performance through a different approach. So in the paper that we'll cover, you will see that there is some flavor of that. Interestingly, you will see so flavor of, let me just write it out. It is not exactly MOE, but it has the flavor of. The other thing you will notice that it has a flavor of is LoRa, low rank adaptation. Right? Now, LoRa adapters essentially say, if you remember, the main message of LoRa is that you take a base model, you leave it frozen, kept frozen, or more generally, PEFT, performance efficient fine tuning. The main approach is that you take the input and you route it to the base model, but you also route it to some auxiliary model, some auxiliary stuff, auxiliary trainable stuff. For example, in the case of LoRa, it is the AB matrix, right? And then what you would do is you would concatenate, you would essentially take the results of both of these to produce your y hat. So that is the whole approach taken by performance efficient fine tuning, and of which LoRa is a dominant example. Now, in this example, the main idea is you can, if you just have to do incremental learning, instead of doing full model fine tuning, you could actually just train an auxiliary model, an auxiliary smaller model. You will notice that in this paper, which is very interesting actually, and I do believe that this may have opened the door to some significant areas of research. Time will tell whether it is very, very recent. It just came out on about 10 days ago. So whether or not it will stand the test of time, but to me, it looked like one of the very insightful breakthroughs that happened recently. So I'll go over this paper now more carefully and show what it does. The gist of this paper is it's a way to scale up models from small to large. As you can sort of annex territory. You want to do more work, you can grow the model organically. One way of looking at it is if you want more functionality in your office, you go and annex more office space, right? Or you annex more, you make an annex to your house for, let's say, running your hobby workshop and so forth. And you can do it without necessarily disrupting your existing house, right? And therein you see the flavor of the LoRa kind of, or PEFT kind of, performance efficient fine tuning kind of thinking going on. But fundamentally, what it says is here is an approach to scale up models, innovative way to scale up models. And the way it does the scaling up of the models, the way it makes it happen is actually a very simple idea. It does one key substitution. In the transformer architecture, it replaces something, a linear projection layer, with yet another kind of attention layer. And what it is, we will go through with that. Actually, it is quite surprising that with just one substitution, they show that you can scale up models very efficiently. You can train a much smaller model and then add more to it without needing to retrain the model, but just bring more data and train the additional parameters. Leave the existing model alone, and you can grow the model organically without losing the learning that the smaller model has gone through from data. So that we will see in this paper. It's very interesting from that perspective. So let's read through this paper now more carefully. The paper says transformers have been the dominant architecture in foundational models due to their excellent performance across various domains. Amma, should you please turn on the air? Transformers have been the predominant architecture in foundational models due to their excellent performance across various domains. We know that, right? Obviously, it's incontrovertible today in 2024. However, the substantial cost of scaling these models remains a significant concern, which is true. Today, the only people who can scale up and make these huge models are the hyperscalers. You're talking about the likes of Meta and Google and OpenAI and so forth. Right? It is not within the means of you and I, normal Joes, to scale up models. Not only not within our means, but it is not even possible, even for companies which are, let us say, merely a few $100 billion of valuation. Right? You need really companies that seem to be valued hugely, close to $1 trillion valuation. That sort of companies seem to have the budget to do significant scaling of foundational models. That's a reality today. So we are looking at two facts. The good news is transformers are the dominant architecture. Neural scaling laws apply to them. The bigger you make them, the more capable they become. On the other hand, the only people who seem to be capable are the people who have significant resources. The cost is huge. So that's the gist of the first two statements. Now, it goes on to say this problem arises primarily from their dependence on a fixed number of parameters. So this is an interesting observation. They claim that they give a cause for the problem, right? So they first state the problem, which we all know. But the interesting thing they mention is it comes primarily from their dependence on a fixed number of parameters within linear projection. So what does that mean? I'll just give you a preview of it. It basically means is that suppose you have an input vector. The fact that we do, given an input vector, what you do is you split it out, embedding vector. E vector, let me just call it E. You produce the K vector, Q vector, and the V vector. And the way you do that is you multiply the input tokens with WK, WQ, WV. And this is something we are, I trust, all familiar with from our understanding of the transformers. This is what they are calling a fixed number of parameters within linear projection. Multiplying by a matrix what they mean by linear projection is that you're multiplied by these matrices, and then you project all of these down to some d-dimensional space, typically. And as you know, in the classic transformer, it was a 64-dimensional space. Right? Now, they continue on to say, when architectural modifications, example, channel dimensions are introduced, the entire model typically requires retraining from scratch. So what they are basically saying is, when you want to do any kind of a change, like add more heads to the multi-head or do anything, then you have to essentially retrain the entire machinery from scratch. So in other words, it's not extensible in the traditional sense. Right? It's not plug-in. You can not annex more or accrete more features into it. As model sizes continue growing, this strategy results in increasingly high computational costs and becomes unsustainable. So it's a point that we have been talking about. To overcome this problem, we introduced Tokenformer. Tokenformer. So this is a new word we introduced, Tokenformer, a natively scalable architecture that leverages the attention mechanism, not only for computations amongst input tokens, but also for interaction between tokens and model parameters, thereby enhancing architectural flexibility. By treating model parameters as tokens. So what do they mean by model parameters? Actually, what they mean is, it's a little bit hard to figure out from the introduction or from just the abstract what they mean. But after reading the paper, you realize that they are looking at these. Because these matrices are essentially parameters of the model, the attention. And then, of course, there is also one more matrix, the output matrix, which we'll come to in a little bit. All of these are model parameters. So they're taking they're pointing it out that that is the culprit. So what they are saying is by treating model parameters as tokens, so these people will take an entirely different approach. They will actually replace the classic W, etc., with something different, with tokens, learnable tokens, right? With our token parameter attention, where input tokens act as queries and model parameters act as key values, right? And this reformulation allows for progressive and efficient scaling without necessitating retraining from scratch. Our model scales from, and this is a point that's really good, impressive. Here, let me highlight it. Our model scales from 124 million parameters, which today is considered a small model, to 1.4 billion parameter by incrementally adding new key value parameter pairs, achieving performance comparable to transformers trained from scratch while greatly reducing training costs. So they have made the code available, by the way, so you can go and look at it. And the code is straightforward. If you're familiar with transformer code, you'll notice that they introduced just one more concept, that of P attention, and we'll cover that. So let's pay attention to what they're saying. They're saying that they took a small model, 124 million parameter model. And then using their way of scaling the model up, they managed to scale it up to 1.4 billion parameter model easily, and they trained it with far less compute cost, right? Because they're increasingly adding parameters. Once some parameters get trained, they add more parameters, and they add more parameters slowly. And as they do that, so in other words, a bigger model just borrows all the parameters of the smaller model and then learns some more. Right? When you take this sort of an approach, then what happens is your total cost of training the model is lower. And when you create a model which is big, it turns out that its performance is the same as if you would have trained 1.4 billion parameter model from scratch, the traditional way, which is bring data, make a big model and train it from scratch, not borrowing parameters from a smaller model. So that is the key point. What they're saying is there is a way to significantly bring down the compute cost of pre-training large models. That is the main contribution. And now the question is, how do they do that? So before they do that, and I'll sort of gloss through some of the background work here. Let's look at the figure one. And I'll sort of explain this in terms of figures. What they are saying is, let's pay attention to this figure. On the left, if we look at this figure, I'll talk our way through this figure. Perplexity is a measure. It is basically the exponentiation of the cross entropy, as you know, average cross entropy loss. It's a measure of how wrong or right the output of a transformer is. Right? So the lower the perplexity, the better it is. Now, in this figure, these balls that you see, these colored circles, they reflect the size of the model. And that you can see from this size of the model. Now, there are two lines that you see here. One line belongs to the traditional scaling of the model, like this one. If you look at this one, it says scale transformers from scratch. Let me make it bigger, actually, so we can see it better. Yeah, scaling transformers from scratch. So that would be the traditional way of doing it. And so when you do it traditionally, what you notice is that as you increase the training cost, or as you increase the compute, then obviously perplexity comes down, right? This looks to you like the normal scaling laws, right? More compute, better model performance. That's good. It plateaus off at some point. But now, let's look at the red one, which is their approach, using the token former. As you can clearly see, to achieve comparable performance, so if you compare what to what, if we compare this one to this one, we notice that they have comparable perplexity. The model performance is good. But if you look at the amount of compute that went into it, the number of TPU hours, the token former achieve the same level of model performance or capability with just 4,000 hours of TPU, whereas the traditional way of using a transformer and training it from scratch would have taken 12,000 hours of training. So clearly, there is a factor of 3 improvement. Right? It will take you 3 times less resources to train a model if you go with the token former approach. And that is the key value proposition of this particular architecture. So the fact that it can do that, and obviously more experiments is needed in multiple areas to see exhaustively how well this holds up in all scenarios. But should this be true, this is quite a significant result. I must say, by the way, I apologize, I didn't mention who the creators of this paper are. This paper seems to be a joint collaboration between 3 heavyweights. You have the Max Planck Institute, of course, a heavyweight in Europe. You have Google, and then you have the Peking University. So obviously, this paper and these researchers there are quite a few researchers here, 1, 2, 3, 4, 5, 6, 7, 8. So it's the collective output of 8 researchers from 3 heavyweight places, academia as well as industry. So, and one of the interesting things you notice is that they take a approach which is quite elegant and simple, and then the main result is that it brings real world practical benefits. So just to whet a recollection of how the traditional transformer works, they have put the traditional transformer and the token former side by side. So please pay attention to the fact that even though the wordings look the same, one is transformer in the middle, the one on the right hand side is the token former. So what is the traditional transformer? Just to remind you, a traditional transformer is basically you take the input again, and you remember that we do the KQV projection. So for example, Q is input times multiplied by WQ times the input embedding would give you the input vector. And similarly for the K and V, you get those vectors. And then when you get those vectors, then you have what is called the self-attention, the famous equation in the attention is all you need paper. And that just once again, I'll just briefly mention because I expect all of us know that attention is K, Q, the inner product scaled up with a square root with a softmax times the V vector, and that is your attention, the attention matrix. And this part, let me just say, this part is often called the score function. So normalized score. So this is your traditional. And then what happens after that? When the attention vector comes out, the attention vector gets multiplied by, well, in a multi-head attention, there's more going on. But just for simplicity, in order to understand this paper, let us assume one attention head, right? Because what applies to one attention head, you can always now concatenate and do projection to multi-attention head. And then you do have this output, and then you bring out a projection of that to get the output. And then you take the output and you feed it through a feed-forward layer, output. You take it and through the feed-forward layer, and from the feed-forward layer, you get the final output of each of the attention heads. What is the final output from that particular attention head, right? So this is the mechanism. This is what we are familiar with, and it has been there more or less intact for the last 5, 6, 7 years now. What they are suggesting is something quite interesting, and let's pay attention to what they are suggesting here. This particular picture, it says that not only the input goes in. Now observe one thing, something is common. You notice that the token attention is there. So we can assume that the self-attention remains. The key part of the transformer remains. But observe something. They have replaced what has been replaced? The KQV projection has been replaced with something called the token parameter attention. So that is the key. One of the key differentiation is this. And not only that, not only input goes in, but you notice that there's some extra things that go in here. Right? So this is new, they go in. And the other thing that goes in, surprisingly, is pay attention here and we'll explain why. Do you notice that in a traditional attention head, things go through a feed-forward network after coming out of the self-attention aspect? It go into feed-forward layers. In this, they replace the feed-forward entirely. What they do is they say that if it is not self-attention, then every single thing, whether it's a non-linear, so feed-forward, you can think of it as a non-linear projection, right? A projection with deformation because of the activation functions and so forth. They're saying no, even that, just replace it with their what they call token parameter attention, or what more going forward they call P attention, the P attention, right? They replace the feed forward layer with P attention, and they replace the KQV projection, which is through those matrices WQ, WV, WK, with the same P attention. So what does it seem to be? If you remark on it, what you see is it is attention all the way. It is either P attention or self-attention, and again P attention. So the entire attention head is re-engineered to be built purely out of attention, with no linear projection, with no feed-forward layer at all. And that is the gist of what they're talking about in this paper. And quite interestingly, so this is the how of it. Why does it work? I will talk about in a moment. Let's go through it. First of all, as a preliminary, they remind you the classic Vaswani's paper, the attention is all you need paper. So let's go back to your attention is all you need. If you remember, this is your attention is all you need paper. And this paper introduced the classic transformer. What was there in the classic transformer? Let us say that you had T tokens. Let's say that you have T tokens. So for brevity, let's take T is equal to 4. So there is, or let's say 7, right? The cow jumped over the moon. Moon, right? And what you're basically doing is, and there's a period here, full stop, 7. So what you do is each of these tokens, obviously you can break it up into word pieces and there's more complexity, but we will oversimplify it a little bit. Ultimately, with position, embedding, position, etc., each of these becomes a vector, embedding vector. E, cow, E jumped, etc., etc., E full stop. It becomes these vectors. These vectors belong to some dimensional space. So each of these vectors belong to d-dimensional space, all of them, right? And therefore, the complete input x is equal to this, the set of all tokens would be, let's say that t is equal to 7 here, you would agree that you're looking at a matrix which is E, cow, etc., etc. So there, it will have size t is equal to 7, and so this will belong to the matrix itself. Therefore, is a set of numbers that belongs to a t times d dimension matrix. That's what the input is to your machinery, right? Now, this matrix, when you multiply with this projection, right? You can project it down to an entirely different dimensional space. Let us say that you take WQ, WK, WV you can project it down. So let's think through this. If you multiply this matrix, X, therefore, X, sorry, let's take a lighter color, X, well, too fat. If you take X times WQ, X is a T cross D matrix, and you multiply it by a matrix which is D cross D output projected, like the key value, key domain, Q thing. Well, in most of the situation, like in the original transformer, for example, this was 24 dimensional. You will get a Q, like Q is equal to this. Q will therefore belong to, there will be a query vector for each of the tokens, and it will belong to this DQ dimension space. Now, typically DQ and DK and D, all of this are 64 dimensional in the original paper, if you remember. So it's a little bit redundant. So now, with that, you come to the so-called attention matrix. Now, in this attention matrix, notice that this is your score, and softmax does what? Softmax essentially does in some sense, L1 norm, exponentiate an N1 norm. If you remember the definition of softmax, it is to do the following. If you get a bunch of numbers, A1, A2, A3, let's say, the softmax is e to the A1, the softmax of, let's say that the normalized, I'll call it S1 is equal to divided by e to the A1 plus e to the A2 plus e to the A3. What's the advantage of this? First of all, it makes sure that all the scores are great, like all the SIs belong to the range 0 to 1. And so this is your L1 norm. Right? The second aspect is that it amplifies the bigger guy. Amplifies the biggest number. You can convince yourself that suppose it is 1 minus 5, 10. Right. So you can see that e to the 1 would be e, 2.7, yeah, approximately. E to the minus 5 would be approximately 0. E to the 10 would be some huge number, right? 8 times, well, let me not take, because then I'll have to figure it out in my head, but let me just make it 4, right? So this would be somewhere close to, let me approximately say about 64 or something like that, somewhere in the order of 64. So you can see that the bigger the 4, this guy gets amplified, the biggest value gets amplified. So, and then it gets normalized and so forth. So anyway, that was the traditional a transformer, you would do that. So your attention vector would pay a lot of attention to that vector where the query was aligned to the key of the vector. That's what it was, right? And square root of D was it. And then what you would do is you had one more W layer. So there are 3 Ws, right? WQ, WK, WV, and now there's an output W. You would take this attention, by the way, you should have literally said X attention. And then you multiply it with a projection, one more projection, to get the output matrix, right? The output result. So this was the attention vector that we are all, the attention theory that we are all familiar with. Now, what are they saying? What is the core idea they say? By the way, in this paper, I suppose it needs a little bit of edit because they keep mixing up the terminology occasionally here and there. Even though it's fairly well written, it takes a little while to realize what is it that they mean. They use 2 terms quite a bit. They use 2, which I will elucidate. They talk about token interaction. Token interaction is basically your attention. So basically your attention is a k dot q square root of d. This is your typical attention is equal to softmax times v, right? So this is each token basically what it means is, and that's the meaning of the self-attention, each token probes other tokens to essentially better get a sense of its own contextual meaning, right? So you feed in a token, and because it pays attention to the neighboring tokens, the output of that, the attention vector in some sense, is a contextualized vector, which is more aware or has picked up color or meaning about itself from its surrounding tokens. That's what that is an intuitive feel for what self-attention means. Right? Then they talk about, so this is the first thing they talk about. Second thing they talk about is token parameter interaction. And they say that the problem is the token parameter interaction. That is what's preventing scaling. It takes a little while, actually, reading this paper carefully to realize that what they're really complaining about are things like the WQ, WK, WV, WO, and they're saying that when you take an input, X, and you multiply it with all of these things, these are linear projections. And because they're linear projections, in some sense, they're limiting or they are not as flexible. And their contention is that let us replace this linear projection also with a form of attention. So while this is self-attention between tokens, they want even this fact, this generation of Q, K, B, and O, which is through this process here, to instead arise through the application of a different mathematical formula, which they call P attention. Right? So basically what they're saying is replace this, with P attention. And that is the core substitution that they are advocating for. So let us try to understand what, and actually paper is very, very small. That's the main idea. And so we can cover it in a few minutes. So let's look at this. I will blow up this diagram here and look at that. They're saying, look at the token. So here, instead of going from the bottom up, they actually have made it top down. So, so it sort of looks inverted, but that's the way they have done it. So you have the input tokens, right? This is your X in normalization. Well, of course we do norm. Norm is one of the steps they do. But pay attention that there is obviously in all of these architectures, there's always a residual link. This is your residual link. In other words, you always go back. So this is your residual. Remember that you do some magic, but you want to make sure that that magic is, the output is not losing information from the input. So what we are saying is, for example, if the cow jumped over the moon, the cow is looking for its meaning about itself, or the word jumped is looking for meaning about itself. It probably understands what jumped means more if it knows that cow did something, and then there's the moon, right? So then what happens is that there is the original meaning of jumped, and then there is the contextualized meaning of jump. And what it is saying essentially is, just when you do a residual connection, and obviously this is sort of going back to the basics, all that the residual connection says is that because I'm giving you the input itself, make sure that whatever this fancy circuit does, it just adds the extra coloring or meaning to the input. Like, what is the additive value this circuit brings, right? And obviously we are going back to the old theoretical notions of residuals and what they are, but I thought I'll bring it out. So that explains this bypass. Now what do? What they are saying is, take the input and create a queue. But when you create the queue, remember, how do you create the queue in ordinary attention? You would have said a queue is equal to x dot wq, right? They are saying, don't do that. Don't do that. Instead, use a mechanism called P attention. That's what we learn. Use a different mechanism to produce KQV or QKV, and then leave the self-attention alone. So this part is the traditional self-attention. Leave it alone. And then what you would do typically is you would take the result of the self-attention. If you go back to the previous paper, previous figure, where's the previous figure? Is it even here? Yeah, here. So you notice that after the token attention, it goes to the feed-forward network. Let me circle that. It goes to the feed-forward network. Once again, they say, forget the feed-forward network, even though it's a nonlinear transformation or projection. Don't do that either. Instead, put a P attention here also. And then when you get the result of all of this, so see, what is this? This is your multi-head attention applied to in this funny way, applied to and producing. Now, let's look at this. We'll understand that. The linear projection of the linear normalization of the input, where is that? That is this part, followed by the multi-head attention. You let it happen, except that you have replaced projections with P attention. You get your output, and then once more, and this is where the notation is actually a bit confusing. It took me a while to get the hang of it. They're saying that the final output of the head is the intermediate output plus the feed forward of the layer normalized thing. So in other words, what they're saying is, where am I? What comes out here is X intermediate, right? Intermediate. You layer normalize it, you attach attention, but this is what they call the F feed forward network. But actually, the confusing thing is it is not feed forward. It is they call it the function, FFN function. Yeah. This FFN operator, let me call it operator, and which I thought was a bit unfortunate choice of terms. It is a replacement for FFN. It is not FFN. In other words, this FFN operator replaces the usual feed forward network layer. Right? They are saying that replace the feed forward layer with this. So that is where I felt that they could perhaps have chosen a different terminology to explain this paper. But now let's understand what they are doing. They are taking the input, normalizing it. Okay, very good. You would. What's the big difference they're doing? All they're saying is replace your W matrices with P attentions. They are no more linear, but they are P attentions. And replace even your feed forward with a P attention. So now let's look at it a little bit more carefully. What is this P attention and how do we understand it? Because that seems to be the crux of the whole paper. So what they bring in is something called key parameter tokens and value parameter tokens. So, and I'll give you an intuition that I thought about and came for this, that see, it is almost like, suppose you have an input. The input goes into a box and all the magic happens. Input tokens. Could you add some more sort of a dictionary of knowledge? Think of it as a knowledge dictionary. That the network has learned. So what would be a dictionary? Some K1, K2, Kn, V1, V2, Vn. And obviously there'll be three replicas of it, one for the query kind, one for the etc., key value kind. But leave that. So imagine that there, and I won't give the superscript, it gets too confusing. So imagine that you have a real dictionary, like the paper book dictionary, in which there are keywords and their thing. What you're basically saying, I think the intuition is that instead of sending just the input tokens, what if we did this game? You treat the input X, you call this the keys, these key vectors, and the value vectors. These are parameter vectors. These are learned vectors. Like imagine that there is a knowledge that the network has learned through training. That is valuable. And what you do is you treat the Q, the X, right off the bat as though it is the Q. If you think of it as some form of a query, what you're looking at, you make the X act as the Q vector of attention, Q of attention, paying attention to, interacting with sort of this external knowledge that with K parameter and value param. You make it pay attention to these things. And so this, of course, is classic cross attention, because a query came from input and KV are sort of machine learned internals, right? So this is obviously cross attention. And this thing they call, they take this, except that they enhance it, they make certain changes. So if it was cross attention, you would say that you would do it like this. XK, you would look at the inner product, right? I think it is X transpose K or XK transpose, one of the two. We can look up the paper, whatever it is. But then what they do is, and then you would expect the same thing as V. If it was just, you would do something like this, right? The scaling parameter. But the journey from this to P attention, which is the core contribution, is something interesting. They are saying, so what is P attention? They create something called P attention. And the formula for P attention is, the first thing they do is they replace softmax with basically GELU function. They replace the, and softmax also does, if you remember the L1 norm, because this is in the definition of the softmax. If you remember, we did that when we do the softmax. Where did we do what a softmax is? Somewhere here. So you notice that this is a L1 norm. You just add up positive numbers at the bottom, divided by that. They are actually saying you replace it with a L2 norm. And why would they do that? Two reasons. Why the substitution? And then they bring in some more modification, which I'll talk about. Why? They say that, see, what softmax does is, if a value is big, let's say I took the value 4, where was it? E to the 4 is already 64. If one of the activations is big, then exponentiating makes it much bigger. And when it becomes much bigger, then you have a problem of vanishing gradients, because what softmax does, they observe on picture, it's true, is that it shapes your distribution, your probability distribution, to a very narrow band focused on the biggest values. All the probabilities are near the big values, right? We know that, if you remember, that is why sometimes you scale the softmax with the temperature parameter. But in the attention, of course, self-attention original formula, you don't scale it by a temperature parameter. But for example, when you do distillation or when you do other things, you tend to dampen it down a little bit, because you do have a problem that it sort of squishes the probability into a narrow band. If it squishes the probability into a narrow band, then what happens is, and you can show it in mathematically, as they show in the appendix, that it tends to create vanishing gradients. Now, one of the most dreaded things while training models is, you don't want vanishing gradients. Why do we not want vanishing gradients? Because it is from the gradients. It is from the gradients that the machine learns, right? Gradients contains the sensitivity of response to input. And therefore, if the gradient itself vanishes, you have no idea what to do with it, like how to make it better, right? And what they find is that instead of using softmax, if you use GELU. Now, what is GELU? GELU function, just to whet your recollection, GELU is nothing but x times the error function. X is what? Fx is nothing but integration of the normal distribution normal distribution, right, e to the, let's say, minus x minus t squared over 2 dt from minus infinity to x. It turns out that this function is, of course, the earth function, is the Gaussian integral, which explains the g here, GELU. And what is the LU stands for? LU is, of course, the linear unit, which is literally y is equal to x, because its shape would be like this, whereas the error function shape is more of a sigmoid. The error function shape would be more like a sigmoid. So this is the phi x shape. So when you multiply these two together, you get a shape that is the GELU shape, which is, I believe this should be a reasonably close approximation to the GELU shape. So as you notice, in a GELU, if you take the derivative, you can clearly see that you won't have a vanishing gradient problem. And in fact, the whole reason ReLUs were introduced, if you remember, going back to the work of Hinton and so forth, long ago, a couple of decades ago, was because you wanted to deal with the problem of vanishing gradients. So one of the things they do, and from experiments they show in one of the tables, that through ablation studies, that you're better off replacing the softmax in the p attention, in this cross attention, with the GELU function and do L2 normalization. That's all, right? You do that, and then you modify that by bringing in a tau factor here. So we will look into that. Let's look into the p attention now more carefully of what it is and what it does. So if you understand that, let's think through it. See, if you are familiar, once again, just for clarity or reference, I will write the old attention just for comparison. The old attention was softmax k x k kq, right? Well, there it was kq, kq, the inner product between these two, with square root of d times v. If you remember, this is what it was, right? Now we agree, or let me write it in the notation that they write it as q k transpose, let's say. And then, so now in our situation, in p attention, they're saying that this gets replaced with, sorry, let me use another marker. A q is the x, that is fine. A k is fine, k is this. V is this, that is fine. So this part is fine and this part is fine, right? Except that they come from the parameters. But softmax is replaced by this function. So let's think about what this function is. What this function is saying that what you do, the way you do the attention, you take the attention and you multiply it by tau, which is just a scaling factor, square root of n, by, again, to stabilize the computation. And then you notice that the denominator, unlike softmax, where you just add up, you take the quadratic norm, like the L2 norm or the Euclidean norm of the attention. That's the only major thing. This is your score function. So that's a bit of mathematics that they bring in. And so this is the main formula for p attention and their scoring function for the p attention. That's all. Now, the rest of the thing is easy to understand. So let's go through the rest of it, if you understand that. So what will they do to create, like, if they don't use the projection matrix, W's are not there, so they will have to create the Q out of P attention, E out of P attention, V out of P attention. That is fine. After that comes the normal self-attention. So this is your normal classic self-attention, the transformer self-attention. So remember, they're not removing it. They are just saying we are replacing the W's, not the attention itself. Token attention is the self-attention. They're not removing it. They are just replacing it, the projection matrices, with P attention, which looks similar, but is a different way of looking at it. And so when they do, and also the output, if you remember, was again a projection matrix, but they say, no, let's do this nonlinear transform, P attention transform, in that. And that's all it is. This paper says, remove all those linear projection matrices and let's put the P attention there. Now, what is the advantage of doing that? The advantage is, suppose you train the machine. So here, let's go back to the intuitive picture we brought. And what the main advantage they're saying is like this. See, suppose you build a model with a certain size K, size A of this sort of size N. So let's say that size is N of this. What just happened? Okay, size N of the key parameter keys and the value parameters. Think of them as a knowledge dictionary that is trainable or learnable that you bring. And now you want to scale the model up from N to, let's say, M. What they are saying is, it is an additive process. It's basically additive. You can, and this is which is self-evident, because if you look at all these formulas, everything is additive. What they are saying is, you want to scale up to more parameters. The easiest way to scale more parameters is just bring more of this parameter keys and parameter values to scale it up. Keep the old one from the smaller model, keep the old one from the smaller model and bring some new ones. Because now this becomes trainable in the second iteration when you make the model bigger. That's all it is. And when you do that, the results they show are pretty impressive. And as you can see, look at the green one. How well incrementally scaling transformers with 15 billion parameter. You took a very small model and you were able to scale and reach a very low complexity comparable to that of an ordinary transformer. You took this token former of 15B parameters and you could achieve very high complexity at a very low compute cost relative to the traditional transformer. So that is the main message of this paper. It contains some, if you're very familiar with the attention formula, and by the way, those of you who have, for example, played with learnable vectors in the case of blip2, Q-former, and things like that, you would see a resonance of that in some sense, these are learnable parameter vectors, keys, values, or matrices that you're injecting. And because you can make these matrices bigger, what they are saying is scale up your models just by bringing in bigger and bigger these trainable or learnable parameters into your model. And when you do that, your model will scale up very well. They show through results that actually it does perform just as well. By the way, they show you this point. Why is it that they replaced softmax with GELU? Because that was a bit of a surprise even for me till I read through the whole paper. And the point that they make is correct, because in the appendix they show the derivation of it. They say that if you, here's the practical result. EX, exponentiation is a L1 norm, right? This is your softmax thing. You get a top, I think this is ImageNet accuracy. ImageNet, you will get classification top one accuracy of 79%. But on the other hand, you just go replace it with L1 GELU. If you replace it with GELU, but still keep L1 norm, you get improvement, 81.7. And if you use GELU, but with L2 norm, then you get 82.5% top accuracy. So that's in the world of ImageNet, these little numbers do matter. It's practically a 2-point improvement in top one accuracy, which is quite good. It proves the point. So this is proving the point in terms of empirical results. In the appendix, they give you a mathematical reason, but because it gets a little bit mathsy, the main point that they make is that when you take the derivative of the softmax, what happens is that the softmax derivative with respect to the attention itself scales as the scores, the individual scores. Now, scores can become sort of big, right? On the other hand, when you look at it, when you look at the derivative, this is their formula here. In contrast, their activation function is normalized. When you do this, it gets normalized. And so they mention comparing the gradients of softmax to our method, the key difference is the gradient depends on Z1, Z2, whereas softmax difference. Due to the exponential nature of softmax, see what happens is when you have unnormalized numbers, exponentiation can become large. And when they become large, your distribution gets narrowed. You can do it with simple numbers, by the way. You don't have to go through this complicated derivation to see it. It is a very, I mean, they have been very formal and very exact to prove the point, but you can more intuitively, we can just put a few numbers down on a piece of paper and exponentiate and see what it means, and you'll see it. So that is that. The other thing they mention is that truly it is additive learning. In other words, when you take a model, let's say of 124 million parameters, and then you go to, let's say, twice the size, or thrice the size, let's say, or whatever, then the learning that you can just copy over all the original weights, the original parameter values. And because all the learning will happen in the new parameters that you introduce in the model for new data. It's almost like, English. A model has only been trained to translate English, and it's a small model, and it does only well with English. Now you want to, you all of a sudden feel that you need to train it to do Mandarin or Korean or Tamil. Then you need a bigger model, you need a bigger brain. But one easy way to make a bigger brain is not to start from scratch, just copy over the English model, scale it up, and then bring data for the additional things. So when you think of it like that, you can clearly see LoRa-like thinking. If you think about LoRa, that was what it was. You fine-tune it in a specific way to get additional benefits. The second aspect that you see is they argue, though I was a bit surprised with this argument, though it's true, that they are saying that you can treat every key and value set, like for example, the old set, the new set, etc. Each of those set pairs as effectively an expert. So the first set became expert at English. Now you bring in another set of parameters, and that, because you're only giving it, let's say, Mandarin data, it becomes very good at Mandarin. So in a way, it represents an internal expert which has the additive Mandarin ability. And then you bring in another one for Korean, and then you bring in another one, parameter set for, let's say, Tamil, and so forth. And so they are saying, in a way of speaking, they're arguing that it has also the flavor of a mixture of experts thinking going on in this paper. Right? So that is what this paper is about. I would strongly suggest that, well, of course, you have to prove the point, and as they prove the point, they show that the perplexity of the model, by slowly growing it in this way, is two benefits. You get to do a lot less compute, because you're not training models from scratch, you're just adding extra sort of knowledge bases or parameters to train. It is almost like adding one more expert or something that they're arguing, that it achieves the same level as a transformer trained from scratch, as you see. Compare the first line and the last line. And so the perplexity, of course, the lower the better. Right? So they are saying that you take a token farmer of 30B parameter and scale it up to 354 million or even 1.4 billion parameters. Right? And what you will notice is that they achieve comparable perplexity, but in other words, you manage to create a really large model, respect the neural scalar, that bigger models are bigger brains, but you didn't pay the compute cost. You paid a lot less compute cost. So that is the key contribution of this paper, right? And that's, I suppose the summarization is that they have found a clever way using something called p-attention. And they're saying, if you replace all your linear projections with p-attentions throughout your architecture, and forget about the feed-forward layer, even your nonlinear deformation, and replace it with p-attention throughout. So then, now, if you think about it, it's sort of a purist approach. Your entire architecture has nothing but attentions. It is either self-attention or the classic self-attention of the original transformer, or it is the p-attention. right? Which also is a form of self-attention, but it's a attention on trainable parameters. So you make your architecture purely out of attention, attention everywhere. No linear projections. No, well, all the key linear projections are gone. All the feed-forward networks are gone. And what you find is that you have a way to scaling up a model without paying the heavy compute cost. That is the main message. Now, as you read this paper, the only point I think I found confusing for a little while, I don't know, maybe you're smarter and you won't have this, is that when I came across this word, FFN, I thought, well, FFN throughout our literature is feed-forward network, but they don't mean feed-forward. They mean it as an operator that replaces the feed-forward. So that is one thing to remember. Other than that, the paper is fairly straightforward to read if you're familiar with the original attention paper, and a remarkable result, I think. Now, the whole question is, what is the price you pay? It seems to be too good to be true, right? In engineering, nothing comes without a price. So what is the price that you will potentially end up paying? Now, the one thing is obviously, uh, if you do this, one is the interpretability. We have taken quite some time to understand the projections. We, so many, for example, if you look at the explanation of attention and transformers on the internet, they will tell you that you project into key space value and then proximity of it and so on and so forth. So obviously it complicates the interpretability a little bit. Perhaps that's a factor, but not by much if you're familiar with attention, very familiar with attention, perhaps you could live with that. There is one thing that I did feel, which is not mentioned in this paper, and I may be completely wrong, but something made me feel that, see, throwing away feed-forward layers may not have been the best idea. I totally like this paper. I like everything about this paper. I would have personally kept the feed-forward layers somewhere. And the reason I would have kept feed-forward layers is feed-forward layers give you, to our knowledge, a way for the transformers to store information. Right? They tend to develop a kind of memory, and they have surprisingly, they sort of act as a model's memory store in some way. And the fact that they removed the feed-forward network altogether makes me worried that how well will it have the ability to remember things? And obviously, subsequent research will show whether my concerns are true or not. But or maybe that memory now gets transplanted into their parameters. These trainable parameters will now start remembering that kind of knowledge base. Quite likely, actually. So my concern may not be valid at all. Because now, instead of feed-forward network, you have all of these trainable, learnable parameters that act as sort of a knowledge augmentation to the input itself everywhere. So maybe that becomes a new place where things or knowledge or memory gets stored. Who knows? I don't know. Right? Maybe somebody will do experiments and find that out. But that was the one and only thought that sort of worried me, because I was thinking, if you remove the feed-forward network altogether, what exactly do you lose? Because we always put feed-forward networks throughout our architecture. We sort of, it's become almost an instinctive habit to, it's almost like between two slices of bread, you put a peanut butter and jelly. Right. And so I don't know. But anyway, who am I? This paper is written by great experts, so most probably they know what they're talking about, or why they can get away removing it altogether. So, well, that is that. That's my interpretation of the paper. Any thoughts, guys? Any thoughts or any ideas anybody has? I don't know. Was it useful, guys? Was it clear, this explanation? Um, I don't hear anything from any.
Oh, yes, Asif. So this was good. I was trying to go through, before the session, I was trying to read through the summary,
Yeah.
and it was good to understand the token to token versus token to parameters interactions. So that was summarized well. So yes, I've got a broad sketch of things, but yes, I need to go through the math of it.
Right, thank you. Anybody else, guys? Anything else before we close today? All right, guys. So if there are no more comments, I'm going to